first thing that survives is not the voice. It is not the name of the builder, or the prayer spoken over the stone, or the order shouted across the worksite as the sun drops behind a line of hills. The first thing that survives is the object, a block cut too cleanly to ignore, a tunnel descending into darkness with a slope so careful that water still remembers the path, a bronze gear lifted from the sea, its teeth green with corrosion. Its purpose almost impossible to believe at first glance. A stone vessel turned so thin that light seems to gather at its rim, a road across a desert, a canal beneath a dead city, a wall so tightly joined that even centuries of wind and weather cannot easily open it. In ruins all over the world, technology remains after the people are gone, and because the people are gone, the technology begins to feel stranger than it may have felt when it was alive. A visitor walking through ancient ruins often meets this strangeness before meeting history. There may be no roof left, no painted walls, no market noise, no smoke from cooking fires, no smell of animals, resin, sweat, oil, and wet clay. There are only stones, foundations, broken columns, fragments of tools, empty channels, and silent spaces. Yet those remains do not look random. They carry intention, they suggest measurement, they show repeated solutions to difficult problems. Someone understood weight, someone understood heat, someone understood the movement of water, the turning of seasons, the strength of timber, the weakness of mud brick, the timing of stars, the value of a straight line, and the danger of getting that line wrong. The ruin becomes a kind of machine after its human operators have disappeared. This is where the mystery begins, not with the idea that ancient people possessed magical powers or impossible knowledge, but with something more unsettling and more interesting. They were far more capable than many later ages assumed. Again and again, archaeology has forced the modern world to lower its sense of superiority. The old story, where progress moves in a neat ladder from primitive confusion toward modern certainty, does not survive long inside an excavation trench. The evidence remains incomplete, but what survives in the record suggests a human past full of experimentation, patience, failure, adaptation, and technical imagination. Some ancient technologies were simple in appearance and brilliant in effect. Others were elaborate, costly, and fragile, depending on whole networks of specialists whose names were never written down. Imagine a landscape before the ruin becomes a ruin. The stones are not pale and lonely, they are new-cut, sharp-edged, dragged into place by teams who know where to place their hands and where not to stand. The canal is not a shallow scar filled with dust. It carries brown water past fields that would die without it. The temple is not merely sacred architecture, it is also a storehouse, an observatory, an office, a workshop, a calendar, and sometimes a bank. The palace is not just a residence. It is a command centre for grain, metal, cloth, soldiers, scribes, animals, and taxes. The city is not simply a crowd of houses. It is an engineered environment, a living system built to hold more people than the surrounding landscape could naturally support without planning. Ancient technology, in this sense, is not only the tool held in the hand, it is the arrangement of the world. Before we go deeper, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy, because the deeper one looks into these ruins, the less the past resembles a dim childhood of humanity, and the more it resembles a long series of solved problems whose solutions were later buried, broken, misunderstood, or forgotten. There is a peculiar kind of silence around ancient technology. Weapons and kings often get names, battles are carved onto walls, victories are exaggerated in inscriptions, gods are praised in stone, but the people who actually made things work usually vanish into anonymity. The surveyor who laid out a wall across uneven ground, the potter who learned exactly how hot a kiln could become before the vessel warped, the metalworker who knew by colour when ore was changing inside a furnace, the shipwright who bent timber into a hull strong enough to cross open water, the scribe who converted sheep, grain, labour, and debt into marks on clay, the water engineer who understood that a tiny miscalculation could drown a field or starve a city. These people rarely stand at the centre of official memory, yet their intelligence is built into the remains. That intelligence can be easy to misread. Modern eyes often separate science, religion, engineering, art, and power into different categories, but ancient societies rarely divided them so cleanly. A monument aligned with the sunrise may be an astronomical instrument, a political statement, a religious stage, and a demonstration of state control all at once. A canal may be a practical irrigation system, but it may also announce that a ruler has imposed order on chaos. A calendar may organise planting and harvest, while also telling priests when to perform rituals and officials when to collect taxes. A bronze mirror may be a luxury object, a technological achievement, a trade item, and a symbol of status. The strange technology found in ruins is often strange because it belonged to worlds where function and meaning were intertwined. This does not mean every mystery points to some lost super-civilization. Many popular claims grow in the cracks where evidence is missing. A heavy stone becomes proof that nobody could have moved it. A precise cut becomes evidence of machines that left no trace. A myth becomes a technical manual. A corroded object becomes a battery, a lens, a power source, a fragment of forgotten modernity. Scholars still debate some objects, and some ruins do preserve unanswered questions. But uncertainty is not the same as permission to invent anything. The true story is powerful enough without turning ancient builders into visitors from elsewhere, or survivors of an imaginary age of electricity and engines. The harder truth is that human beings are using materials close at hand and knowledge passed through generations, achieve things that still demand respect. Consider the difference between impossible and unfamiliar. A massive stone block may look impossible until one studies sledges, rollers, ramps, levers, packed earth, wet clay, rope, labour organisation, and the immense patience of societies that could command seasons of work. A precisely oriented temple may seem supernatural until one watches the horizon for years and learns how shadows, stars, and solstices repeat. A mechanical device from the ancient Mediterranean may feel out of place until it is placed among traditions of geometry, astronomy, bronze casting, gear cutting, and philosophical curiosity. The shock comes not because the evidence violates history, but because it expands it. The ruins ask for a slower kind of attention. They ask us to see technology not only as electricity, steel towers, glass screens, and engines, but as any disciplined method by which humans extend their power over matter, time, distance, memory, and nature. A stone blade is technology, fire control is technology, a granary is technology, a writing system is technology, a calendar is technology, a road, a sewer, a loom, a furnace, a pulley, a seal, a sail, a scale, and a map are all technologies. Some leave spectacular remains, others disappear almost completely because they were made of wood, fibre, leather, wax, or knowledge held only in trained hands. No single explanation fully accounts for what survives and what vanishes. The archaeological record is not a complete library. It is a burnt archive with many missing shelves. And yet enough survives to disturb the old assumptions. In Egypt, stone vessels from early dynastic and even pre-dynastic contexts show astonishing control over hard materials long before the Great Pyramids rise. In Mesopotamia, clay tablets reveal counting systems so detailed that they turn ancient temples into information machines. In the Indus cities, drainage and standardized bricks suggest an urban order whose governing structure remains difficult to reconstruct because its script is still undeciphered. In the Andes, roads and masonry climb mountains where modern visitors struggle simply to breathe. In the Mediterranean, a lump of corroded bronze from a shipwreck eventually reveals itself as a geared model of celestial cycles. Each example belongs to its own world, but together they make one point clear. Ancient technology was not a single miracle, it was a long human habit. The story begins before cities, before monuments, before the first scribe presses a reed into wet clay. It begins with hands, stone, fire, and attention. It begins with the moment a human ancestor sees not only what a rock is, but what it can become. The silent machines of the ruins are late chapters in a much older story, and to understand why they still feel strange, the path has to lead backward first, into the deep time where invention begins without writing, without kings, and without any certainty that it will be remembered at all. Long before a city wall casts its shadow across a crowded street, long before bronze flows into moulds, long before a ruler claims that the gods have granted him mastery over land and water, technology begins in a far quieter place. It begins beside a scatter of stones, it begins in the pause before a hand strikes one rock against another, it begins with a mind that can imagine an edge hidden inside a lump of flint, quartzite, obsidian, or basalt. The first machines are not machines in the later sense. They do not turn on axles or measure the heavens with gears. They are extensions of the body, sharpened by intention. A hand becomes more than a hand when it holds a cutting edge. Teeth become less necessary when stone can slice hide, tendon, and meat. A small tool changes the shape of survival. This is the deeper foundation beneath every strange artifact found in later ruins. The astonishing devices of antiquity did not appear from nowhere. They grow out of an extremely long apprenticeship between human beings and the material world. For millions of years, different human ancestors and relatives learn how stone breaks, how bone splinters, how wood bends, how fire behaves, how animals move through landscapes, how seasons return, and how memory can be stored in habit even before it is stored in writing. Scholars still debate the full timeline of these developments, and the evidence remains incomplete because the oldest technologies were often made from materials that decay. But what survives is enough to show that invention is not a sudden gift of civilization. It is one of the oldest human behaviours. A stone tool may seem humble beside a pyramid or an aqueduct, but it contains a surprising chain of decisions. The maker must choose the right stone, carry it, strike it at the correct angle, understand force without naming it, anticipate the shape of the flake before it breaks away, and often repeat the process many times without shattering the core. This is not random smashing. Even the earliest known stone tool traditions show patterns, preferences, and learned technique. Later, hand axes, with their balanced forms and careful edges, reveal something almost meditative and mind-shaping matter toward an imagined result. Some are practical, some are so finely made that archaeologists have wondered whether they also carried social or symbolic meaning. No single explanation fully accounts for every example, but the tools themselves make one thing clear. Long before written engineering, there is already planning. Fire deepens the story. It is difficult to overstate how much changes when humans learn not merely to encounter fire, but to keep it, move it, feed it, and eventually make it. Fire softens food and extends the range of what can be eaten. It hardens wooden spear tips. It gives warmth in cold places and light against predators. It changes social life because flame draws bodies together after dark. Around fire, time stretches. The day does not simply end when the sun is gone. Skills can be taught. Food shared, stories remembered, warnings passed on. Fire is a technology of chemistry, but also a technology of community. It turns the night into a room. The strange thing is that so much of this early knowledge leaves only faint traces. A burned patch of sediment, charcoal in a cave layer, heat-fractured stone, microscopic wear on an edge. The absence of evidence is not always evidence of absence, especially in deep prehistory, where rain, soil, scavengers, erosion, and time erase most human activity. What survives in the record suggests that early humans lived inside a technical world far richer than the scraps imply. They likely made cords, nets, baskets, simple traps, digging sticks, carrying slings, shelters, and clothing long before most of those things could be preserved. A fragment of fibre or a mark in clay can hint at entire lost industries of plant, skin, and wood. The ruin of deep time is not a temple with fallen columns. It is a silence where almost everything organic has vanished. This matters because later ancient technology often appears strange when only the durable pieces remain. Stone survives and looks eternal. Metal survives, though altered by corrosion. Fired clay survives in huge quantities. But the ropes that lifted the stones, the wooden frames that held machines together, the leather bellows that fed furnaces, the wax tablets that carried calculations, the reed boats, the scaffolds, the measuring cords, the baskets of earth used to build ramps. All these can disappear. The surviving object then seems isolated, almost miraculous, because the temporary world that made it possible has gone. The earliest technologies teach the same lesson. Human skill is often larger than the material trace it leaves behind. The body itself is part of this ancient technology. A skilled flint knapper does not need a written formula to know when a blow is wrong. A hunter does not need a map to read slope, wind, dung, broken grass, and bird alarm calls. A gatherer does not need a botanical chart to know which root poisons, which heals, which must be soaked, which changes with the season. Knowledge lives in muscles, scars, stories, and repeated gestures. In modern terms, it may not look like machinery, but it is a technical system tested, corrected, transmitted, and refined. The earliest human worlds are filled with expertise that would be almost invisible if one looked only for metal gears or polished stone walls. Over time, tools become more specialised. Blades grow thinner. Points are shaped for throwing or thrusting. Bone needles appear, suggesting fitted clothing and the ability to live in harsher climates. Grinding stones reveal the processing of seeds and pigments, shell beads, ochre, carved objects, and painted caves show that technical skill is not limited to survival alone. Humans are making signs, colours, ornaments, and images. They are modifying not only the environment, but identity and memory. A bead is a small technology of belonging, pigment is a technology of presence. A painted animal on a cave wall is not a machine, but it depends on material knowledge, minerals ground into powder, binders, brushes, lamps, surfaces, and the confidence to place an image where darkness had been. The surprising detail is how early humans often solved problems by combining materials. Composite tools, where stone points are attached to shafts with bindings and adhesives, require several kinds of knowledge at once. Resin, plant fibre, sinew, heat treatment, stone shaping, and woodwork all come together in a single object. This is a quiet revolution. A stone flake alone is useful, but a point fixed to a shaft changes reach, force, and danger. It also shows an ability to think in systems. The power of the tool lies not in one material, but in the relationship between materials. Much later, the same principle will govern chariots, ships, furnaces, water systems, and astronomical mechanisms. Complex technology begins when separate skills are made to cooperate. By the end of the Ice Age and into the warming world that follows, human communities are already carrying vast libraries of practical knowledge without writing a word. They understand landscapes through movement. They know migration routes, stone sources, waterholes, animal behaviour, edible plants, seasonal dangers, and the social rules that keep groups alive. When some communities begin to settle more permanently, cultivate plants, manage animals, and build larger ritual or domestic spaces, they are not stepping out of ignorance into invention. They are redirecting a very old intelligence toward new problems. Sedentary life creates possibilities, but also pressures. Stored food must be protected, fields must be tended, houses must be repaired, dead ancestors may remain close. Boundaries matter more. Time becomes more scheduled. Labour becomes more concentrated. Out of that pressure, the path bends toward the first villages and then toward cities. Technology begins to gather weight. It moves from the hand to the household, from the household to the settlement, from the settlement to the landscape. The blade, the hearth, the basket, and the digging stick do not vanish. They remain underneath everything, but above them, new systems begin to rise walls, granaries, shrines, canals, kilns, and eventually the administrative machinery of civilization. The ruins that later seem so mysterious are built on this long foundation of hands learning the world one material at a time. When people begin to live together in larger numbers, technology changes character. It no longer belongs only to the hand, the hearth, or the small group moving through a familiar landscape. It becomes something heavier, more organised, and more demanding. A village can survive with memory, custom, and shared labour, A city cannot. A city needs systems. It needs food arriving from beyond its streets, water moving where nature did not place it, waste carried away before it poisons the living, walls repaired before enemies arrive, workshops supplied with raw materials, and records kept because no single mind can hold all the obligations that bind thousands of people together. In this moment, ancient technology begins to resemble an engine, not because it has pistons or steam, but because many moving parts must work in rhythm or the whole structure falters. The earliest cities are not simply bigger villages, they are experiments in density. In southern Mesopotamia, where some of the world's first urban centres grow from the flatlands between the Tigris and Euphrates, the environment offers both promise and threat. The soil can be astonishingly fertile, but rainfall is unreliable. River channels shift, floods can destroy, and fields may turn salty when irrigation is poorly managed over long periods. To live there at scale requires more than planting grain. It requires canals, embankments, drainage, labour coordination, storage, and authority. A city like Uruk does not rise only from mud brick. It rises from scheduling, measurement, and the ability to persuade or compel large numbers of people to maintain artificial landscapes. The city is an invention, and it is also a machine for making inventions necessary. In such places, even ordinary materials become part of large technical systems. Mud is not just mud, mixed with straw, shaped into bricks, dried under the sun, and stacked by the thousands. It becomes walls, platforms, houses, temples, and administrative buildings. Clay is not just earth, pressed into tablets, marked by reeds, and dried or fired. It becomes memory. Reeds become mats, baskets, boats, writing tools, roofing, and measuring rods. Bitumen becomes waterproofing for vessels and brickwork. Grain becomes food, tax, wage, offering, debt, and political power. The surprising detail is that many of the technologies that make early cities possible are not spectacular in isolation. A brick is simple, a basket is simple, a seal is small enough to fit in the hand, but when multiplied across a city, these ordinary tools form a system more powerful than any single monument. Writing grows out of this pressure. Long before literature, royal inscriptions, and myths are written down, marks are used to track things: sheep, jars, fields, rations, labour days, deliveries, and debts. The first information systems are deeply practical. They are technologies of accountability. A clay tablet can outlast the spoken promise. A seal impression can identify a person, office, or institution. A token can stand for an object not physically present. This is one of the great transformations in human history, but it begins with bookkeeping, which is perhaps less romantic than a divine revelation and far more revealing. The earliest cities need ways to remember beyond memory, and so they make memory external. The ruin later gives us broken walls and broken tablets, but in life those tablets help to keep the walls supplied with workers and materials. The city also concentrates specialists. Farmers still matter, more than anyone, because without surplus food there is no urban life, but inside and around the city, potters, smiths, scribes, builders, brewers, weavers, merchants, boatmen, soldiers, priests, and administrators become part of a widening web of dependency. Skills sharpen when people can devote more time to them. A potter who fires vessel after vessel learns the moods of clay and heat. A metal worker who handles ore, charcoal, and furnace conditions discovers possibilities that cannot be reached by casual experiment. A scribe trained for years learns signs, numbers, formats, and institutional habits that turn writing into professional power. The evidence remains incomplete because workshops are often reused, disturbed, or destroyed. But what survives in the record suggests a world of disciplined labour, where technology is held in communities of practice rather than in isolated flashes of genius. Cities need standardisation. Bricks of similar size make construction faster. Weights and measures make exchange more trustworthy. Containers of known capacity make storage and distribution easier. Roads and gates shape movement. Calendars help coordinate planting, harvesting, ritual, and taxation. Time itself becomes more organised. In smaller groups, the season may be known through plants, animals, and weather. In cities, time must also be administered. Workers receive rations. Festivals recur, debts mature, fields are assessed, ships depart when river conditions allow. The calendar becomes a tool of both survival and control. Scholars still debate how much central authority governed different early cities, and the answer varies by place, but the technical need for coordination is unmistakable. This is why ruins can feel like dead machines. A great temple platform is not merely a sacred mound. It is the visible centre of a system that draws in grain, animals, labour, offerings, craft goods, and political loyalty. A palace is not only a residence for elites, it is a hub of record-keeping, storage, redistribution, diplomacy, and force. A city gate is not only an entrance, it is a checkpoint, a tax point, a defensive structure, and a symbol of belonging. Even streets become technologies. Channeling humans, carts, animals, wastewater, and processions through planned or semi-planned spaces. When those systems stop working, the walls may remain, but the engine is gone. Later visitors see the shell and wonder how it was built, forgetting that the deeper question is how it was maintained. The Indus cities offer one of the most intriguing examples of urban technology that does not fit simple expectations. At sites such as Mohenjo-Daro and Harappa, there are standardized baked bricks, carefully laid streets, wells, bathing areas, and impressive drainage systems. Many houses appear to have access to water and drains, suggesting a concern with urban cleanliness unusual in scale and consistency for the ancient world. Yet the political structure behind this order remains difficult to identify. There are no clearly understood royal inscriptions, no obvious palaces towering above everything else, and the script remains undeciphered. No single explanation fully accounts for how such standardization was achieved across wide distances. What survives suggests strong shared conventions, skilled planning, and social organization, but not necessarily the same kind of king-centered system familiar from Egypt or Mesopotamia. In Egypt, technology takes another path shaped by the Nile. The river floods in rhythms that are more predictable than the rivers of Mesopotamia, though never perfectly obedient. Agriculture, transport, taxation, and royal ideology all gather around the river's cycle. Boats move stone, grain, officials, soldiers, and messages along a natural highway. Mud brick towns and stone monuments belong to the same civilization, but survive very differently, which can distort the modern view. The stone temple endures, the worker's house crumbles, the royal tomb dazzles, the wooden tool rots. Yet the great monuments depend on all the less durable systems beneath them: bakeries, breweries, copper tools, rope-making, sledges, ramps, quarries, scribal administration, and the bodies of skilled labourers who know how to move in coordinated teams. As cities rise, the strange technology of ancient ruins becomes less a collection of isolated marvels and more a pattern. The marvel is not only that a stone was moved, a drain laid, or a tablet inscribed. The marvel is that entire societies learned to coordinate materials, people, landscapes, and time. The ancient city is a human-made environment that must constantly be repaired against decay. Walls crack, canals silt, wells foul, roofs collapse, grain moulds, records become outdated. Tools wear down, animals die, workers resist, rulers overreach. The machine of the city needs constant attention, and when attention fails, even the most impressive system can begin to come apart. But while cities create new kinds of technology, they also create new kinds of ambition. Once people learn that landscapes can be organised, water redirected, labour measured, and stone raised into permanent forms, they begin to build not only for use, but for memory. They build toward the sky, toward the horizon, toward the gods, toward death, toward political immortality. Out of the city engine comes the monument, and in the monument ancient geometry begins to speak in stone. The stone monuments are the easiest to misunderstand because they survive too well. Their makers are gone, their scaffolds are gone, their ropes are gone, their temporary ramps and work camps and shouted instructions have dissolved into dust. But the stone remains with an almost unfair confidence. It stands in deserts, on plains, on islands, in mountains, and beneath forests that grew over abandoned walls. It outlives the tools that cut it and the hands that placed it. It outlives the language that named it, and because it remains while so much else has vanished, it begins to look as if it never truly belonged to ordinary human life at all. A carved block weighing many tons lies in place, and modern imagination rushes toward impossibility before patience has a chance to speak. Yet stone is not magic. It is stubborn matter, and ancient builders learned its habits through long practice. They learned which rock fractures cleanly, which crumbles, which can be polished, which carries weight, which splits along a bedding plane, and which must be abandoned even after days of labour because a hidden flaw has ruined it. Quarries are among the most revealing ancient sites because they preserve the unfinished side of monumentality. In a finished temple or pyramid, everything appears inevitable. In a quarry, the process has exposed tool marks, extraction trenches, abandoned blocks, ramps, roads, chips of waste stone, and sometimes the ghost of a project that failed before it could become impressive. What survives in the record suggests that ancient stone technology was often less about secret machinery than about accumulated experience, organised labour, and an intimate understanding of material weakness. Precision masonry creates one of the deepest sources of wonder. In Egypt, the casing stones of pyramids once formed smooth plains that caught the sun with a brilliance mostly lost today. In the Andes, Inca walls fit irregular stones together so tightly that their joints appear almost fluid, though they are made of hard rock. In the eastern Mediterranean, Mycenaean builders raised massive fortification walls that later Greeks thought must have been made by giants. On islands such as Malta, Neolithic communities built megalithic temples with enormous stones long before metal tools were common there. Across different regions and periods, people found ways to measure, align, lift, drag, trim, polish, and set stone with an accuracy that still carries emotional force. Scholars still debate some details of technique in particular cases, but the broader pattern is clear given time, skilled observation, and social organisation. Human beings can make stone behave in surprisingly disciplined ways. Geometry is the hidden technology inside many of these monuments. It does not need to appear as written equations to be real. A builder laying out a right angle with chords, stakes, and repeated measurements is using geometry. A surveyor levelling a foundation by water, sight lines, or plumb tools is using geometry. A mason shaping blocks so that weight presses downward and inward rather than outward is using practical mathematics. even if the knowledge is carried as craft rather than theory. In ruins, geometry becomes visible because it is frozen into walls and alignments, a straight passage, a level platform, a repeated module of bricks, an axis aimed toward a horizon event. All these are traces of minds thinking through space. The temptation is to imagine that such precision must require modern instruments, but ancient precision does not always mean modern precision, and it does not always need modern tools. A shadow cast by a vertical rod can mark directions in the movement of the sun. A stretched cord can create a line. A plumb bob can reveal vertical truth more honestly than the eye. Water seeks level with a patience no ruler can command. Repetition improves accuracy. Error can be corrected through checking and rechecking. For builders who work over years, sometimes generations, the sky and the landscape become measuring instruments. No single explanation fully accounts for every alignment claimed at ancient sites, and some popular claims are exaggerated, but many monuments do show careful attention to celestial or cardinal orientation. That attention does not diminish the mystery, it makes it more human. One of the lesser-known details in ancient construction is how much of it depended on temporary works that were never meant to survive. A pyramid is visible, its ramps are debated because they were dismantled, reused, eroded, or built from materials less durable than the monument itself. A standing stone is visible, the timber frames, earthen banks, hauling tracks, and feasting camps that supported its raising may be faint or gone. A temple wall is visible, the wooden scaffolding. Lifting devices, baskets, sledges, and rope systems disappear. Ancient engineering often hides behind the success of its final product. The better the temporary technology worked, the less likely it was to remain as a dramatic ruin. This is especially important when thinking about so-called impossible stones. Large blocks are not moved by strength alone. They are moved by reducing friction, distributing labour, preparing routes, controlling pace, and making the work socially meaningful enough that people will continue. In some ancient Egyptian scenes, teams pull heavy statues on sledges while a worker pours liquid before the runners, likely to reduce friction on the ground. Experimental archaeology has shown that sledges, rollers in some contexts, levers, ramps, and coordinated teams can accomplish tasks that seem unreasonable when imagined as individual effort. The real technology is not only the device, it is choreography. It is the conversion of many human bodies into one controlled force. Monumental building also depends on food. This may seem less glamorous than stone cutting, but it is fundamental. A workforce must eat, tools must be supplied, injured workers must be replaced or cared for, specialists must be trained, seasons must be chosen. In Egypt, large labour projects could be tied to agricultural rhythms, especially times when flood conditions limited fieldwork. At other sites, feasting appears to have played a role in gathering and motivating communities for construction. The monument is therefore not only an engineering project, it is a social event, a political statement, and a logistical achievement. A stone raised upright may represent faith or authority, but beneath it lies bread, beer, meat, rope, timber, planning, and the quiet mathematics of supply. Astronomical alignments add another layer. Some monuments frame solstice sunrises or sunsets. Others appear connected to lunar standstills, cardinal directions, or culturally important stars. The purpose is rarely just observation in the modern scientific sense. The sky's timekeeper, sacred order, agricultural guide, royal symbol, and cosmic map. A passage that admits sunlight on a particular day can turn architecture into an event. A temple axis can link a ruler to divine order. A stone circle can bring the horizon into a designed relationship with memory and ritual. The evidence remains incomplete at many sites, and not every alignment is intentional, because with enough stones and enough horizon points, coincidence can masquerade as design. Still, the best supported cases show that ancient builders could turn architecture into a calendar. The wonder of these structures is not that they violate the limits of their age, it is that they reveal those limits being pushed with extraordinary persistence. Stone demanded planning over long periods. It demanded specialists who could see the final shape before it existed. It demanded communities willing to move weight not because it was easy, but because permanence mattered. And perhaps this is why stone technology still grips the imagination. It is the most visible form of ancient confidence. It says that a society believed its gods, kings, ancestors, or civic identity deserved to outlast the bodies that served them. But stone, for all its endurance, is only one side of the ancient technological mind. Beneath many ruins runs another kind of intelligence, harder to see at first, but often more essential to survival. It is found in channels, drains, tunnels, wells, reservoirs, and carefully managed floodplains. If stone shows the ambition to be remembered, water shows the struggle to remain alive. The next great ancient technology does not stand still in the sun. It moves, leaks, rises, dries, floods, and has to be commanded again and again. Water is the ancient engineer's most difficult partner because it is never truly obedient. Stone resists, but it stays where it is placed if the builder understands weight well enough. Water does not. It seeps through cracks, carries silt, rots foundations, breeds disease, vanishes into sand, rises without warning, and turns from blessing to catastrophe in a single season. A society may carve its authority into stone, but it proves its endurance through water. The strange technology hidden beneath ancient ruins often lies not in the walls people admire, but in the channels they step over without noticing. The drains beneath vanished streets, the wells cut through deep earth, and the reservoirs that once held a city's future in their basins. To control water is to control time. Rain falls when it chooses. Rivers flood according to rhythms that may be generous one generation and destructive the next, and drought has no respect for kings. Irrigation changes this relationship. It allows fields to drink when clouds do not come. It makes surplus possible in places where dry months would otherwise shrink harvests. But irrigation is never simply a canal dug once and forgotten. It is a living technology. Channels silt up, banks break. Water must be divided among fields, and that division can create cooperation, resentment, law, and violence. The evidence remains incomplete in many early irrigation landscapes because canals are rebuilt, erased, buried, or mistaken for natural channels. But what survives in the record suggests that some ancient societies were shaped as much by water management as by warfare or belief. In Mesopotamia, water brings civilization and danger together. The rivers make agriculture possible on a grand scale, yet they also shift, flood, and leave salts behind when irrigation water evaporates from the fields. Over time, salinization can reduce yields, especially when drainage is poor and cultivation remains intense. Scholars still debate the scale and timing of environmental stress in different Mesopotamian periods, and no single explanation fully accounts for the rise and fall of its cities. But water management was never a background detail. It was central. A canal was not merely an engineering feature, it was a political artery. Whoever maintained it, guarded it, allocated it, and repaired it held power over bread itself. The same is true in Egypt, though the Nile offered a different kind of bargain. Its annual flood was more predictable than the rivers of southern Mesopotamia, and this predictability helped shape Egyptian agriculture, taxation, transport, and cosmology. Yet even there, too little flood meant hunger, too much meant destruction, and the river's gifts still required basins, embankments, canals, measuring systems, and administrative attention. The Nilometer, used in various forms to gauge the river's height, was a deceptively simple technology with enormous consequences. A mark on stone could help anticipate harvest levels, tax expectations, and potential crisis. In a world where water height could become political fate, measurement itself became power. Far from the great river valleys, ancient water technologies become even more surprising. The Qanat, developed in arid regions and widely associated with ancient Iran and surrounding areas, carries groundwater through gently sloping underground channels from uplands towards settlements and fields. Its brilliance lies in its restraint. Instead of lifting water with constant labour, the system lets gravity do the work, protecting the flow from evaporation beneath the surface. Building one requires careful surveying, knowledge of geology, and dangerous excavation through vertical shafts. A Qanat is not dramatic like a pyramid, but for communities on dry land it can be more miraculous in practical terms. It turns hidden water into a quiet, durable lifeline. Wells are equally easy to underestimate. A deep well is a vertical argument against thirst. It requires knowledge of where water might be found, the ability to cut or line a shaft safely, and a system for lifting water repeatedly without collapse or contamination. In some Indus cities, wells appear in remarkable numbers, integrated into neighbourhoods and houses, while drains carry wastewater away through brick-lined channels. The result is not a modern sanitation system, but it is a sophisticated urban water culture. Mohenjo-Daro's so-called Great Bath, with its carefully fitted bricks and waterproofing, shows not only technical skill, but also the social importance of controlled water. Its exact ritual or civic function remains debated, yet the structure itself reveals a society that knows how to make water stay where it is supposed to stay. Drainage may be the least glamorous of ancient technologies, but it's among the most revealing. A city that cannot remove wastewater is a city slowly poisoning itself. Drains, sewers, soak pits, street gradients, and covered channels show a concern with the unpleasant realities of density. The ancient world did not always solve these problems well, and many cities must have smelled far worse than their surviving ruins suggest. But where drainage systems do appear, they reveal planning that reaches below the visible surface. In ruins, drains can seem like minor features compared with temples and palaces. In life, they may have mattered more on an ordinary day than any royal inscription. Water also builds and destroys through storage. Reservoirs, cisterns, and tanks allow communities to survive dry seasons, sieges, and uncertain rainfall in the Maya lowlands, where great cities rose in environments with seasonal water stress and limited permanent surface water in many areas. Reservoirs and other water management strategies were essential. Archaeologists continue to refine the details of how different Maya cities captured, stored, filtered, and distributed water. The evidence suggests impressive adaptation, though not invulnerability. When drought, political strain, warfare, and environmental pressure converged, even elaborate systems could fail. Ancient water technology could extend resilience, but it could not abolish risk. The Romans later make water control one of the signatures of imperial life. Aqueducts carried water across valleys, through tunnels, and into cities using gradients so carefully calculated that the flow could continue over long distances without pumps. The visible arches have become symbols of Roman engineering, but the most important work often happened in less spectacular forms: channels, settling tanks, distribution basins, lead or ceramic pipes, maintenance shafts, and legal systems governing use. An aqueduct was not just a structure, it was an institution in stone, mortar, and law. It required surveyors, builders, inspectors, cleaners, and political will. Without maintenance, even Rome's greatest waterworks would become elegant ruins. There is a deeper lesson in all these systems. Water technology forces ancient societies to think beyond the moment of construction. A monument can be built and left to impress. A canal cannot. A drain cannot. A reservoir cannot. It must be cleaned, watched, repaired, defended, and negotiated. This makes water one of the clearest places where technology and society become inseparable. The tool is not only the channel, but the community that keeps the channel open. The machine is not only the aqueduct, but the offices and workers that prevent it from silting, cracking, or being stolen from piece by piece. And when that social machine breaks, water quickly reclaims its freedom. Canals clog, fields dry or turn saline, reservoirs fill with sediment, drains back up, wells become contaminated or abandoned. Cities that once seemed permanent begin to lose the invisible systems that made permanence possible. The ruins then preserve a paradox: the stones may stand long after the water has stopped flowing through the logic that gave them life. Yet water is only one element ancient people learned to command. Another transformation happens in heat, where mud becomes ceramic, sand becomes glass, ore becomes metal, and colour becomes permanent on walls and vessels. If water teaches patience and maintenance, or a fire teaches change, it takes ordinary matter and makes it something else. Fire is the oldest transformation humans learn to trust, but in the workshops of the ancient world it becomes something more controlled, more dangerous, and more exacting. A campfire warms and cooks, but a furnace changes the identity of matter. Clay goes in soft and comes out hard enough to survive millennia. Ore goes in as stone and comes out as metal. Sand, ash, and mineral additives become glass. Pigments are fixed to plaster. Glazes shine on ceramics. And blackened fuel turns hidden chemical possibilities into tools, weapons, ornaments, vessels, and symbols of power. To stand near an ancient kiln or furnace is to stand near a boundary. On one side is nature as found. On the other is nature forced to become useful. The earliest fired clay objects already reveal a remarkable leap. Clay is forgiving when wet, but unforgiving after firing. A potter must understand texture, moisture, temper, wall thickness, drying time, airflow, and heat. Too much water and the vessel cracks. Too little preparation and it explodes in the kiln. Uneven heat warps the form. Poor clay fails. A successful pot is therefore not just a container, it is a controlled event, in settled communities. Pottery changes daily life because food can be stored, cooked, transported, fermented, and measured in new ways. A jar can hold grain against hunger, beer against thirst, oil against decay, and offerings against forgetfulness. Archaeologists often find pottery in great abundance because fired clay survives so well, but that abundance can hide how revolutionary it once was. A broken sherd may look humble, yet it can carry fingerprints, trade routes, diet, chronology, and the habits of an entire household. Kilns make heat into architecture. A simple open firing can harden clay, but more advanced kilns allow higher temperatures, better oxygen control, and more reliable results. The potter learns the colour of heat, the sound of fuel, the draft of air, the behaviour of smoke. These are not abstract principles written on a wall. They are embodied skills, learned by watching failure. Scholars still debate how quickly different firing techniques spread and how much was discovered independently in different regions. But the pattern is unmistakable once humans learn to build chambers for heat. They begin to open doors into new materials. The kiln is a quiet ancestor of later industrial worlds. Metallurgy pushes this transformation further. Native metals such as gold and copper can be hammered into shape, and their beauty must have drawn attention long before people understood ores. Gold resists corrosion and seems almost outside ordinary decay, which helps explain its power in elite burials and sacred objects. Copper is more practical, but pure copper is soft compared with later alloys. The real transformation comes when people learn that certain stones contain metal hidden inside them, and that heat, fuel, and controlled conditions can separate it. Smelting is one of the most astonishing inventions in human history, because it requires belief in something invisible. The desired material is not obvious on the surface. It must be imagined inside the ore, then coaxed out through fire. Bronze, made by alloying copper with tin or sometimes other elements, changes the ancient world not because it is magical, but because it combines hardness, castability, durability, and beauty in ways stone and pure copper cannot. It can become axes, chisels, swords, spearheads, mirrors, bowls, statues, fittings, and ceremonial objects. But bronze also creates dependency. Copper and tin are not always found together. Tin, in particular, can require long-distance exchange. A bronze tool may therefore contain a map of trade hidden inside its metal. The object found in a ruin may look local because it was used locally, but its ingredients may have crossed mountains, deserts, rivers, and seas. What survives in the record suggests that metallurgy helped bind distant regions together, making technology a matter of networks as much as workshops. Iron brings another set of challenges. It is common in the earth but difficult to master because it requires high temperatures and careful working. Early iron objects are sometimes rare and prestigious, Before iron becomes everyday, meteoric iron, fallen from the sky and containing nickel, appears in some early objects, giving them an aura that must have seemed extraordinary. Later bloomery furnaces produce spongy masses of iron that must be hammered to remove slag. This is laborious, smoky, and physically demanding work. The blacksmith becomes a figure of practical importance and sometimes social unease, because he stands beside heat, noise, sparks, and transformation. He makes ploughs and knives, but also weapons. He deals with the hidden strength of the earth. Ancient steel-like materials add another layer of complexity. In parts of South Asia, high-carbon crucible steel, often discussed under the broad historical label of woots, became famous for producing blades with remarkable qualities when properly forged. The details of production varied, and later legends often exaggerated the mystery, but the underlying achievement was real control over carbon. Heat and cooling could change the behaviour of iron dramatically. The evidence remains incomplete because recipes were transmitted through practice. Workshops vanished, and later observers did not always understand what they were seeing. Yet the surviving objects and textual hints show that ancient craftspeople could manipulate materials at a level that feels surprisingly advanced, even when their explanations differed from modern chemistry. Glass is another kind of captured fire. It looks like frozen water, but is born from heat intense enough to fuse mineral ingredients. Ancient glassmaking likely develops through long experimentation with faience, glazes, furnace conditions, and raw materials such as silica, natron, and lime. Early glass objects are precious, often used for beads, inlays, vessels, and elite display. Colour is controlled through metallic compounds, whether intentionally or through impurities: blue, green, yellow. Black and deep red glass carry not only beauty but chemical knowledge. A glass bead in a tomb may seem decorative, but it represents furnace technology, trade in raw materials, specialised labour, and an understanding of heat that could not be guessed in a single attempt. Pigments and surface technologies also belong to this story. Egyptian blue, one of the earliest synthetic pigments, required heating silica, copper compounds, calcium, and alkali under controlled conditions. It was not simply groundstone, it was manufactured colour, glazes on ceramics, faience amulets, painted tombs, frescoes, polished plasters, and mineral cosmetics all show ancient people experimenting with permanence and appearance. They did not only make tools to survive, they made surfaces that shone, bodies that signalled status, gods that glimmered, and rooms that turned light into authority. Technology here becomes emotional and political. A blue crown, a gilded mask, a red painted wall, a black stone statue polished like still water, all use material skill to shape belief. The surprising truth is that many ancient technologies were discovered without a modern theory of atoms, molecules, or thermodynamics. Craftspeople did not need those concepts to produce reliable results. They worked through observation, repetition, secrecy, apprenticeship, and tradition. They knew that one ore behaved differently from another, that one fuel burned hotter, that one furnace draft changed the outcome, that quenching could harden, that annealing could soften, that impurities could ruin or improve a result. Their knowledge was empirical, not primitive. It was tested by consequences. A failed casting wasted metal, a cracked pot wasted labour, a weak blade could cost a life. Fire technologies also leave behind some of the most puzzling archaeological traces because workshops were places of intense reuse. Furnaces were rebuilt, slag heaps accumulated, broken moulds were discarded, tools were recycled. Valuable metal was melted down again and again, which means many ancient objects vanished not through decay, but through usefulness. Gold from one king could become jewellery for another, bronze statues could become weapons, copper tools could become new tools. The archaeological record of metal is therefore deeply uneven. What survives may be what was lost, buried, sacrificed, wrecked, hidden, or forgotten. No single explanation fully accounts for what remains and what was remade beyond recognition. This makes the technologies of heat feel like messages from vanished workshops. A corroded blade, a slag fragment, a glass bead, a kiln scar in the earth, a blue pigment on a wall, a mould for casting a small figure. All are traces of people who learned to persuade matter to change form. They did not conquer nature completely. Furnaces failed, mines collapsed, fuel ran out, and metals created new hunger for resources. But in fire, ancient societies found a way to make the hidden visible. Stone could become copper, earth could become ceramic, sand could become glass, colour could become nearly permanent, and once matter could be transformed, another transformation became possible. The ancient world also learned to transform memory. Clay tablets, seals, numbers, calendars, and archives turned speech into durable signs. The next strange technology is quieter than a furnace, but in many ways even more powerful, because it allowed human commands to outlive the human mouth. The first written marks do not appear as poetry, they do not arrive as philosophy, sacred scripture, or a king's proud account of conquest. They begin, in many places, with things, animals, jars, measures of grain, workers, fields, rations, debts, deliveries, and obligations. Before writing becomes a voice for myths and laws, it is a device for keeping track. It is a technology that allows memory to leave the body and sit in clay, bone, wood, stone, ink, or wax. A spoken order fades unless someone remembers it. A mark remains. It can be counted again. It can be carried to another room. It can accuse, confirm, authorize, or preserve. In this quiet shift, ancient society invents one of its strangest machines, the archive. The earliest information systems grow out of practical pressure. A small community may remember who owes what, which field belongs to which family, and how many animals are moving with a herd. A city cannot depend on memory alone. Temples, palaces, workshops, and storehouses need records because scale produces forgetfulness. Grain goes in, grain goes out, workers receive rations, cloth is assigned, animals are born, sacrificed, traded, or lost. Land must be measured, labour must be scheduled. Officials must be checked by other officials. The clay tablet becomes a tool as real as the plough or the chisel. It does not cut earth or stone, but it cuts confusion into categories. In Mesopotamia, the development from tokens and sealed clay envelopes to impressed and incised tablets reveals a long experiment in external memory. Small counters may represent sheep, jars, or quantities. Seals mark ownership or authority. Clay bulle enclose tokens, and their outer surfaces carry impressions that identify what lies within. Eventually, the logic shifts. If marks on the outside can represent the contents, the tokens inside become less necessary. The mark itself can stand for the thing. This is not a simple invention by a single genius in a single room. It is a gradual reorganization of thought. What survives in the record suggests that accounting, administration, and symbolic representation grow together, each step making the next one easier to imagine. A seal is a particularly elegant piece of ancient technology because it combines art, identity, security, and bureaucracy in one object. Cylinder seals in Mesopotamia, rolled across wet clay, leave miniature scenes and identifying impressions. Stamp seals elsewhere perform similar tasks. A sealed jar, door, basket, tablet, or package can show whether it has been opened or tampered with. The seal turns clay into a witness. It also turns authority into a repeatable mark. The person may be absent, but the impression remains. In a world without digital signatures, passwords, or printed labels, seals do an astonishing amount of work. They are small objects, often beautiful, but their practical force is immense. Numbers are another hidden technology of the ancient ruins. Counting seems obvious only because it is now so deeply familiar, but different kinds of counting are needed for different kinds of things: grain, land, labour, animals, time, silver, cloth. Some early systems use different numerical conventions depending on what is being counted, which can feel strange to modern minds trained by uniform arithmetic. Yet such systems make sense inside their own administrative worlds. Measurement is always cultural as well as mathematical. A unit of grain, a day of labour, a length of field, a weight of metal, all become standardised enough to be recorded, compared, taxed, and exchanged. Once number attaches itself to the world, power can travel through ledgers. Calendars extend this control into time. Farmers had always watched seasons, but administrative societies needed time that could be shared across institutions. Rituals had to happen when they were expected. Taxes had to be due. Labour rotations had to begin and end. Markets, festivals, planting, harvest, navigation, and royal ceremonies all depended on predictable cycles. Ancient calendars were not always perfectly aligned with solar or lunar realities, and many required adjustment, observation, or priestly interpretation. Scholars still debate the details of some ancient calendrical systems, especially where texts are fragmentary, or later reconstructions are uncertain, but the general importance is clear. A calendar is not just a way to know the date, it's a way to make society move together. Archives, when they survive, offer a different kind of ruin from broken walls. A palace archive may contain letters, inventories, legal decisions, diplomatic messages, omen reports, school exercises, contracts, and lists so ordinary that they feel almost startling. In some cases, archives are preserved by disaster. Fire that destroys a building may bake clay tablets hard enough to survive for thousands of years. This is one of archaeology's darker ironies: destruction can become preservation. A room burned in war or collapse may turn perishable administration into durable evidence. The people who fled or died would not have considered this fortunate, but the modern record sometimes depends on catastrophe. The information systems of ancient Egypt show a different material world. Papyrus, made from the papyrus plant, allowed writing on light, portable sheets, but it survives mainly in dry conditions. This means the Egyptian record is both rich and uneven. Tombs, deserts, and sealed contexts preserve what wetter environments destroy. Scribes used ink, palettes, brushes or reed pens, ostraca, wooden boards, and stone inscriptions, depending on purpose and prestige. Monumental hieroglyphs carved into temples and tombs give an impression of eternal sacred writing, but everyday administration depended heavily on more fragile materials. Much of that vanished. The result is another distortion. The official voice in stone survives loudly, while the routine machinery of daily record-keeping often survives only by chance. Writing also changes the human mind's relationship with distance. A message can travel without the speaker, a command can reach a province, a treaty can bind rulers who are not face-to-face, a list can coordinate supplies before an army moves, a legal document can preserve a dispute after witnesses are gone. This does not mean ancient states were perfectly efficient. Far from it. Messengers were delayed, Officials cheated, tablets were misread, archives were lost. And orders could fail in the mud of real life. No single explanation fully accounts for how ancient administrations functioned across all regions and periods. But writing gave institutions a new kind of reach. It made absence manageable. There is also a more intimate side to this technology. School tablets preserve mistakes. Practice exercises show hands learning signs through repetition. Some tablets contain copied proverbs, word lists, and model contracts, traces of students being trained into the discipline of scribal culture. The scribe's work may look dry from a distance, but it required years of effort and gave access to a powerful social world. To write was to enter the machinery of temples, palaces, courts, and trade. It was also to become part of a tradition that could preserve knowledge beyond the lifespan of any teacher. The stylus, like the chisel or the furnace, created specialists. Undeciphered scripts remind us how fragile information technology can be. The Indus script remains unread. Despite many attempts, Linear A from the Aegean still resists full understanding. Other writing systems are known only through fragments. A script can survive physically and still remain silent if the language behind it is unknown, the corpus too small, or the key missing. The evidence remains incomplete, and the silence is not romantic emptiness but technical loss. A tablet or seal may be covered with signs and yet deny us its meaning. The information system has outlived its users but lost its operating instructions. This is why ancient writing belongs among the strange technologies of ruins. It is not merely communication, it is storage, control, identity, proof, schedule, memory, and power. It lets a temple count sheep it cannot see. It lets a ruler command workers he will never meet. It lets merchants trust weights and contracts beyond kinship. It lets astronomers record cycles, doctors list remedies, priests preserve rituals, and later generations read the concerns of people who never imagined us. And once memory could be stored, measured, and transmitted, and the sky itself became a kind of archive. The movements of the sun, moon, planets, and stars could be watched, recorded, predicted, and built into ritual life. The next technologies do not sit only in storerooms and offices, they rise into temples, instruments, shadows, and machines of sacred time, where science and belief are not rivals, but two languages spoken under the same ancient heavens. The sky is the oldest clock that never stops running. Long before gears, written tables, observatories, or royal calendars, people lived beneath a ceiling of moving lights that return with a discipline unlike anything on Earth. The sun shifts along the horizon through the year, the moon changes shape, disappears, returns, and governs the night with a rhythm both familiar and unsettling. Certain stars rise before dawn only in particular seasons. Planets wander against the fixed background, sometimes reversing their course in ways that seem almost deliberate. To ancient observers, the heavens are not empty space, they are order made visible, a vast turning pattern above a world where rivers flood, rulers die, crops fail, and cities burn. It is no surprise that some of the strangest technologies found in ruins are technologies of timing. At first, the instrument may be nothing more than attention. A person watches the place where the sun rises for many years and learns that it does not rise from the same point every morning. It travels along the horizon, reaches an extreme, turns back, and begins again. A vertical stick casts shadows that shorten, lengthen, and shift direction. A notch in a ridge, a standing stone, a temple doorway, or a line between two posts can become a marker. This is not astronomy in the modern institutional sense, but it is careful observation, repeated across seasons and generations. The evidence remains incomplete because many early sky-watching practices left few physical traces, yet what survives suggests that ancient communities used architecture, landscape, and memory together to keep time. The practical reasons are obvious. Planting, harvesting, animal migrations, wet and dry seasons, sailing conditions, and ritual gatherings all depend on timing. But practical need alone does not explain the emotional force of ancient sky technologies. The sky is also sacred order. If earthly life is unstable, the heavens seem to offer a pattern beyond human argument. A ruler who aligns a monument with a celestial event does more than show technical skill. He places authority inside a cosmic frame. A community that gathers when sunlight enters a chamber or touches a carved stone is not simply checking a date. It is watching the universe confirm that time has turned as expected. In such moments, architecture becomes a device for making the invisible cycle visible. This is where modern categories can mislead. It is easy to ask whether an ancient structure is scientific or religious, practical or symbolic, astronomical or political. Often it is all of these at once. A temple may orient toward a solstice sunrise, not because its builders are detached scientists, but because the sun's movement matters for agriculture, kingship, ritual renewal, and the story a society tells about its place in the cosmos. A calendar may help organize taxation and labor while also marking sacred festivals. An omen text may seem irrational by modern standards, yet the careful recording of celestial events inside such traditions could preserve valuable observational data. Scholars still debate how to interpret many alignments and records, but the boundary between belief and measurement is far less rigid in ancient ruins than it is in modern textbooks. In Egypt, the sky is woven into architecture and royal ideology. The cardinal orientation of major pyramids shows impressive surveying ability, and some pyramid passages and temple axes appear connected to celestial or solar symbolism. The annual rising of Sirius, associated with the coming Nile flood in Egyptian tradition, links star observation with agricultural expectation and sacred time. The details changed over long periods, and no single explanation fully accounts for every alignment or ritual association. But the broader pattern is unmistakable. Egyptian builders and priests watched the sky not as a distant abstraction, but as part of a living system that joined river, calendar, death, kingship, and eternity. In Mesopotamia, celestial observation becomes increasingly textual. Generations of scholars record eclipses, planetary movements, lunar phenomena, and omens on clay tablets. Their interpretations are often embedded in divination, but their records show disciplined attention to repeating patterns. Over time, Babylonian astronomers developed mathematical schemes capable of predicting celestial cycles with remarkable success. This does not mean they practiced astronomy exactly as a modern observatory does. Their goals, assumptions, and cosmology were different. Yet the technical achievement is real. They made the sky calculable through records, numbers, and inherited tables. The heavens became an archive that could be read forward as well as backward. Other regions show different forms of sky technology. In Mesoamerica, Maya calendar systems combine cycles of ritual, solar time, and long historical reckoning. Their inscriptions and codices, where they survive, reveal sophisticated attention to cycles of Venus, eclipses, and calendrical relationships. The Maya did not need telescopes to create complex timekeeping. They needed long observation, mathematics, scribal tradition, and cultural reasons to care deeply about recurrence. The destruction of many manuscripts and the fragmentary survival of others mean the record is painfully incomplete. But enough remains to show that time itself could become monumental. A date carved in stone was not just a label. It placed an event within layered cycles reaching backward and forward across vast spans. Shadow instruments carry this same impulse in simpler form. Gnomons, sundials, merkets, sighting tools, and horizon markers all turn light into information. A shadow is fragile, vanishing as soon as it appears, but when compared against a marked surface or repeated observation, it becomes data. The beauty of such devices lies in their economy. They require no engine. The sun supplies the movement, the instrument supplies the frame. Ancient technologies often work this way. Not by overpowering nature, but by arranging a situation in which nature reveals something useful. A water clock uses flow, a shadow clock uses light, a star calendar uses recurrence. The device is simple because the universe is doing most of the work. Ritual machines also belong here, though they may look strange to modern eyes. Some temples are built so that sunlight reaches a sanctuary on certain days. Some sacred landscapes arrange pathways, sight lines, and monuments to create processions through cosmic space. Some portable instruments, like astrolabes in later antiquity and the medieval world, allow users to solve problems of time and position by modelling the sky on a disk. Earlier devices were often less durable or less fully preserved. But the desire is ancient to hold a piece of the heavens in the hand, to make the sky small enough to use. The most surprising thing about these technologies is not that ancient people watch the sky. Everyone sees the sky. The surprise is the patience required to turn seeing into knowledge. A single lifetime may not be enough to recognise all cycles clearly. Eclipses, planetary periods, lunar standstills, and calendrical corrections demand accumulated records and institutional continuity. Someone must watch, someone must remember, someone must teach. And someone must care enough to preserve the pattern. This makes astronomy a social technology as much as an intellectual one. The observatory is not only the platform or instrument, it is the chain of observers across generations. But this chain can break. A war destroys archives, a priesthood loses status, a script becomes unreadable, a city is abandoned, a calendar is replaced, a device corrodes beneath the sea. Then later ages discover fragments and wonder how far the knowledge once went. The ruins preserve hints of sky systems whose full operating logic may be partly lost. The evidence remains incomplete, and that incompleteness has invited both careful scholarship and wild invention. But the real achievement remains visible enough ancient people learned to turn the heavens into time, authority, prediction, and sacred order. And then, in one astonishing case, they turned the heavens into gears, not merely shadows, not merely alignments, not only tables pressed into clay or dates carved into stone, but bronze wheels with teeth, rotating together inside a device small enough to be carried by human hands. The sea damaged it, time disguised it, and at first it looked like little more than a corroded lump. Yet inside that lump waited one of the most startling technological survivals from the ancient world. The object comes from a shipwreck, and that matters. It does not emerge from a royal tomb, displayed with intention. It is not found in a temple where its meaning can be supported by inscriptions, offerings, or ritual setting. It lies for centuries beneath the sea, near the Greek island of Antikythera, among statues, amphorae, luxury goods, and the scattered cargo of a vessel that sinks in the 1st century BCE. Salt water enters everything, wood disappears, bronze corrodes, forms collapse into crust. By the time sponge divers and later investigators bring fragments to the surface, one of the most extraordinary machines of antiquity looks, at first, like a ruined mass of greenish metal and marine growth. Its strangeness is hidden not by secrecy, but by damage. The Antikythera mechanism is shocking because it compresses the sky into machinery. It is not simply a decorative object, and it is not merely a symbolic model. What survives shows interlocking bronze gears, inscriptions, pointers, scales, and a design intended to calculate and display cycles of the sun, moon, eclipses, and calendar time. Later imaging has revealed details invisible to the naked eye, including gear teeth, internal structure, and text engraved on the fragments. The evidence remains incomplete because much of the device is missing, and scholars still debate certain reconstructions, functions, and details of its original display. But the central fact no longer depends on speculation. This was a complex-geared astronomical calculator from the ancient Greek world. Its importance lies partly in how lonely it seems. Before the mechanism was understood, many people assumed that such intricate gearwork belonged to a much later technological age. Simple gears were known in antiquity, and mechanical devices existed. But the density and sophistication of this object forced historians to reconsider what Hellenistic engineers and astronomers could achieve. It does not prove that the ancient world was full of hidden factories or modern machines. It does something more precise and more unsettling. It proves that, under certain conditions, ancient craftspeople could combine mathematical astronomy, bronze working, fine mechanical design, and skilled assembly into a portable device of remarkable complexity. To imagine it when new, one has to strip away the sea. The bronze is not a fused ruin, but carefully shaped. The gears turn, the inscriptions are legible. The user handles a wooden case with front and back displays, perhaps turning a hand crank or knob that sets the mechanism in motion. Pointers move across scales, cycles align. The moon's irregular motion is modelled with mechanical ingenuity. Eclipse predictions appear according to known cycles. Calendrical systems are brought into relation. The machine does not observe the sky directly like a telescope, which ancient people did not possess. It calculates from inherited astronomical knowledge. In that sense, it is not a window, but a memory engine, a device that stores mathematical relationships in metal. This makes the mechanism part of a broader intellectual world. Hellenistic astronomy inherited and transformed ideas from earlier Greek, Babylonian, and Egyptian traditions. Babylonian observers had recorded celestial phenomena for centuries and developed powerful numerical methods for predicting cycles. Greek thinkers explored geometry, models of planetary motion, and mechanical explanation in cities such as Alexandria, Rhodes, and others tied into Mediterranean networks of learning. Mathematics, craft, and patronage could meet. The Antikythera mechanism belongs somewhere in this world of scholars, instrument makers, navigators, elites, and collectors. Its exact maker is unknown. Its workshop is lost. Its owner is uncertain. What survives in the record suggests a technical culture more capable than the single surviving object can fully reveal. That loneliness is one of the central mysteries. Was the Antikythera mechanism unique, a masterpiece made by an exceptional workshop for an elite patron? Or was it one example of a class of devices that mostly vanished because bronze was valuable and machines were fragile? No single explanation fully accounts for its survival. Bronze objects were often recycled. A device that broke could be melted down. A mechanism kept on land might be destroyed by fire, corrosion, looting, or reuse. This one survived precisely because it was lost in a shipwreck, sealed away from human recycling even as the sea damaged it. The absence of many comparable finds does not necessarily mean such devices were unknown, but it does warn against imagining a vast lost industry without evidence. The mechanism also reveals the gap between written knowledge and material survival. Ancient texts mention mechanical wonders, automata, celestial globes, water devices, and instruments associated with famous engineers and thinkers. Hero of Alexandria, writing later, describes devices powered by steam, water, air pressure, and weights, though many were designed for demonstration, temple spectacle, or clever display rather than industrial production. Archimedes was associated in later accounts with spheres or models showing celestial motions. Some descriptions are difficult to interpret, and later traditions can exaggerate. Yet the Antikythera mechanism proves that at least some complex devices were not literary fantasies. Fine mechanical astronomy existed in bronze. Still, it is important not to misunderstand the shock. The mechanism is not a computer in the modern electronic sense, although it is often called an ancient analog computer, because it uses mechanical relationships to calculate and display information. It does not imply electric power, lost digital science, or industrial manufacturing. Its gears are handcrafted, its logic is astronomical and calendrical, its power comes from human turning, not from an engine. But calling it less than modern does not make it less extraordinary. In some ways, its achievement is sharpened by its limitations, with bronze, wood, inscriptions, gear ratios, and inherited sky records. Ancient makers created a compact model of time. The device also shows how technology can be shaped by cultural desire. Why build such a thing? It could have served education, elite display, calendrical calculation, astronomical demonstration, or perhaps several purposes at once. It may have helped show when eclipses were expected, where the sun and moon stood in cycles, and how different calendars related. It might have impressed viewers as much as informed them. In the ancient Mediterranean, knowledge of the heavens carried philosophical, religious, navigational, agricultural, and political significance. To own a machine that made celestial order move under the hand was to possess not the sky itself, but a privileged model of it. One lesser-known detail is that the inscriptions appear to function partly like operating instructions or explanatory labels. This matters because the mechanism was not self-evident. It needed a literate user, or at least a trained one. Ancient technology often depended on such layered access. A plough can be understood by watching it work. A geared astronomical calculator requires a technical culture around it, makers who can build it, users who can interpret it, and a society that values what it displays. When that culture disappears, the object becomes almost unreadable. Its gears remain, but their meaning has to be reconstructed tooth by tooth. The Antikythera mechanism therefore stands at the centre of the story, not because it proves that ancient technology was secretly modern, but because it reveals how much can vanish when craft traditions break. A whole lineage of instruments may leave only one wrecked survivor. A workshop may disappear without a foundation stone. A tradition of calculation may survive in texts, but not in devices. A machine may spend 2,000 years disguised as corrosion before imaging. Patience. And scholarship bring it back into view. The ruin is not only the shipwreck. The ruin is the broken chain of knowledge between the maker's hand and the modern eye. And this leads to a larger problem. Many ancient technologies seem to appear suddenly because the missing steps were made of perishable materials, recycled metals, vanished workshops, and knowledge passed mouth to ear, hand to hand, master to apprentice. The Antikythera mechanism is not just a marvel, it is a warning about the incompleteness of survival. If one machine like this can almost disappear, how many quieter technologies have left no recognizable trace at all? The past often looks more sudden than it was. A device appears in the archaeological record, and because the earlier experiments have not survived, it seems to arrive without ancestors. A city reveals drainage, but the generations of trial that taught people how water moves under streets are mostly gone. A bronze blade lies in a grave, but the failed castings, broken moulds, apprentice errors, and exhausted furnaces have been swept away or recycled. A stone monument stands with clean authority. But the wooden machines that helped raise it have rotted into the soil. The record gives us peaks without always preserving the slopes that led to them. This is one reason ancient technology feels strange. We are often looking at the last visible result of an invisible process. Workshops are among the great missing places of ancient history. Some survive as floors stained by fire, slag heaps, broken crucibles, discarded moulds, drill cores, misfired pottery, chips of stone, or concentrations of tools. But many workshops were temporary, reused, cleaned, rebuilt, or destroyed by later occupation. A smith's workplace might leave only slag and furnace remains, while the metal objects he made were carried far away, repaired, traded, buried, or melted down. A carpenter's skill might be central to building ships, roofs, scaffolds, chariots, and machines, yet wood decays in most environments. A rope maker could be essential to moving stones, raising sails, drawing water, and binding loads, but rope survives only under exceptional conditions. The evidence remains incomplete not because nothing happened, but because most working life was made from vulnerable materials. This loss is especially important for mechanical technology: gears, pulleys, levers, cranes, water-lifting devices, lathes, looms, presses, and measuring instruments often depend on wood, cordage, leather, wax, and small metal fittings. If the metal is valuable, it is removed and reused. If the wood rots, the shape of the machine disappears. If the device was common, people may not have buried it carefully or described it with awe. The ordinary can vanish precisely because it was useful until the end. A broken bronze statue might be melted, a worn tool might be reforged, a damaged cart might be stripped for parts, a wooden frame might become fuel. What later survives is not a fair sample of what once existed. It is a biased accident. Ancient craft knowledge was also often guarded in bodies rather than books. A master potter teaches by correction, not by writing a complete manual. A mason knows the sound of a stone when struck. A dyer recognizes the moment a colour is taken. A glassmaker watches the furnace atmosphere through changes in glow and smoke. A shipwright understands curves by eye, hand, and inherited pattern. These skills can be extraordinarily precise without becoming textual. When a craft tradition is interrupted by war, migration, economic collapse, resource loss, or changing taste, the knowledge can disappear quickly. The tools may remain for a while, but without trained hands, they become mute. There are hints of these missing links in unfinished objects. An unfinished statue shows how a figure was roughed out before polishing. A partially cut obelisk reveals quarrying methods and the disaster of a crack appearing before completion. A broken mould shows how metal was poured. A kiln full of failed pots preserves a day when heat betrayed the potter. These failures are precious because they show process. Finished objects hide labour. Failed objects confess it. They remind us that ancient technology was not a chain of miracles, but a field of experiments. Some successful, many abandoned. Scholars still debate specific techniques at many sites, but the broad picture is one of repeated testing, adaptation, and practical memory. The missing links are not only physical. Sometimes the social conditions that made technology possible vanish as completely as the tools. A major building project requires food surplus, leadership, skilled planners, labour organisation, transport routes, and belief in the project's purpose. If those conditions disappear, the technology may technically remain known, but it can no longer be used at the same scale. People may still understand how to cut stone, but no longer have the political or economic structure to quarry, transport, and place enormous blocks. They may know how to maintain canals, but conflict or depopulation may leave too few workers to clear them. They may remember how a device was made, but the patron who could pay for it is gone. This is one reason decline can be misread as forgetfulness. A society does not always lose knowledge because people become less intelligent. Often it loses the networks that make knowledge usable. The best bronze caster cannot work without ore, fuel, tools, apprentices, and demand. The finest scribe cannot preserve archives if the palace burns and the language of power changes. The engineer cannot maintain an aqueduct if the administrative system that pays maintenance crews collapses. No single explanation fully accounts for technological loss across all ancient cultures. But again and again, the survival of technology depends on institutions as much as inventions. Trade networks create another kind of hidden ancestry. A glass bead found far from its production centre may appear as a local mystery until chemical analysis links it to distant materials. A bronze object may contain tin from a remote source. A carved stone may travel hundreds of miles. Techniques spread with merchants, captives, migrants, marriages, soldiers, and wandering specialists. Ruins can look isolated today because the roads, harbours, boats, and human relationships that connected them have disappeared. In life, many ancient sites were not lonely at all. They were nodes in moving systems. Even ideas travelled in forms that leave little trace. A visiting craftsman might teach a technique and leave no name. A conquered city might supply specialists to an empire. A marriage alliance might carry luxury objects and the people who know how to make them. A copied design might be adapted until its origin is hard to recognise. Ancient technology is therefore not just local genius or central invention. It is often a braid of borrowing, imitation, adjustment, and independent discovery. What survives in the record suggests that people were constantly watching one another's solutions. This makes the sudden appearance of advanced objects less mysterious, but not less fascinating. The Antikythera mechanism, a fine steel blade, a complex drainage system, a precisely cut stone vessel, or a perfected ceramic glaze may stand at the end of a long road whose earlier milestones were destroyed. Archaeology sometimes recovers those milestones, sometimes it does not. The responsible answer is neither to deny the achievement nor to fill the gaps with unsupported fantasy. The better approach is to imagine the missing workshop's smoke-dark rooms, tool racks, wet clay floors, apprentices sweeping debris, masters correcting angles, traders delivering raw materials, scribes recording supplies, and unfinished experiments waiting in corners. The ruins remember results. The workshops remembered methods. Between them lies one of the deepest silences in ancient history. And from that silence, another truth begins to emerge. Technology does not stay in one place. Once a technique works, it moves. It follows roads, rivers, pack animals, ships, soldiers, pilgrims, merchants, and refugees. The next layer of the story is motion itself. Because ancient technology was carried through networks that made distant worlds part of one another long before modern maps made them seem close. A road is a technology of trust. It says that someone has passed this way often enough to make passage easier for the next traveller. At first, it may be nothing more than a worn path across grass, a line of compressed earth between fields, a track around marshland, or a route from water to shelter. But as societies grow, roads become deliberate. They are cleared, levelled, paved, guarded, measured, repaired, and sometimes monumentalised. They turn distance into something more manageable. They allow grain, stone, timber, soldiers, messages, taxes, pilgrims, and ideas to move with greater predictability. A road does not glitter like gold or astonish like a geared mechanism. Yet without roads, many ancient wonders would remain local accidents, unable to gather the materials, people, and knowledge that made them possible. The wheel belongs to the same transformation. Though its history is less simple than it first appears, it is easy to imagine the wheel as an obvious invention, but obvious inventions are often obvious only after someone has made them. A wheel requires more than a round shape. It requires an axle, a frame, suitable materials, roads or surfaces where rolling is useful, animals or people to provide force, and a society that needs the kind of transport it makes possible. In some regions, wheeled vehicles become central to farming, trade, and war. In others, geography, terrain, available animals, or different transport traditions limit their importance. The evidence remains incomplete in many early cases, but what survives suggests that the wheel's power was not universal by itself. It became powerful when joined to roads, draft animals, carpentry, and social demand. Carts and wagons changed the scale of land transport, but they also created new technical problems. A wheel must be strong enough not to split, light enough to move, and shaped precisely enough to turn without destroying its axle. Solid wheels are durable but heavy. Spoked wheels require more advanced woodworking and design, but allow speed and manoeuvrability. Axles must be lubricated, loads must be balanced, animals must be harnessed without choking or injuring them. A vehicle is therefore not one invention, but a bundle of inventions cooperating under strain. When archaeologists find a wheel, a rut, a model cart, or a chariot fitting, they are seeing only fragments of a larger system that includes forests, workshops, roads, animal breeding, and maintenance. The chariot shows how transport technology can become political theatre. Light, fast, and difficult to build well, chariots spread across parts of the ancient Near East, Egypt, the Aegean, South Asia, and beyond in different forms and periods. Their military role has sometimes been overstated or simplified, because terrain, tactics, and context mattered greatly, but their symbolic role is unmistakable. A ruler in a chariot is not merely moving, he is displaying speed, command, status, and access to specialised craft. The vehicle depends on carpenters, wheelwrights, leather workers, horse trainers, metal workers, and stable systems. Its presence in art and burial tells us that motion itself could become a mark of elite power. Yet the greatest ancient highways were often water. Rivers carried weight more easily than roads. A boat could move loads that would exhaust teams of animals on land. The Nile, the Euphrates, the Tigris, the Indus, the Yellow River, the Mediterranean, the Red Sea, the Indian Ocean, and countless smaller waterways all functioned as corridors of technology. Ships carried stone for monuments, cedar for palaces, copper, tin, wine, oil, grain, ivory, incense, glass, slaves, soldiers, and stories. Harbours and river landings were not merely edges of settlement, they were interfaces between worlds. A city with water access could breathe through trade. Boat building is one of the most underrated ancient technologies because wood rarely survives well. Where it does survive, the skill can be extraordinary. Planks must be shaped and joined, hulls must balance flexibility and strength, seams must be sealed, sails must be woven, ropes twisted, masts stepped, oars fitted, anchors designed, cargo secured, and crews trained to read wind, current, stars, coastlines, birds, clouds, and colour changes in water. A ship is a floating society of materials. It is also a risk machine. Every voyage carries the possibility of storm, piracy, reef, rot, hunger, thirst, and miscalculation. The Antikythera mechanism survived because one such machine failed and sank, turning a commercial disaster into a future archaeological revelation. Maritime trade also spreads technologies in ways that are difficult to trace. A pot style appears on a distant shore, a weight system is adopted, a metal alloy changes, a writing sign travels with merchants, a religious symbol moves along with sailors, glass beads reach inland communities, spices, resins, and luxury goods carry not only scent and colour, but news of other worlds. No single explanation fully accounts for every pattern of exchange, because trade can be peaceful, forced, seasonal. Elite-controlled, informal, or embedded in migration, but the movement itself is undeniable. Ancient ruins that seem remote today were often tied into networks of astonishing reach. Road systems could also become instruments of empire. The Persian royal road, Roman roads, Inca roads, and other imperial routes made administration faster and military response more effective. Roman roads are famous for their layered construction, drainage, paving, milestones, and durability, though not every Roman road was a perfect stone highway. Their real significance lies in the way they integrated provinces into a system of movement. The Inca road network, stretching across mountains, deserts, valleys, and high plateaus, shows a different genius, built in a world without wheeled transport for practical hauling and without horses before European arrival. It served runners, caravans of lamas, armies, administrators, and ritual movement. Suspension bridges of fibre cross terrifying gorges, renewed through communal labour. Such bridges remind us again how much ancient infrastructure has vanished because it was made of organic materials. Measurement travels with networks. Standard weights allow strangers to trade with less suspicion. Coinage, where it develops, turns metal into portable authority. Written contracts allow goods to move through trusts supported by law or custom. Seals protect cargo, calendars coordinate departures, maps and itineraries, whether drawn, written, or memorized, help compress distance into sequence. A trader may not need a modern map if he knows the next well, the next pass, the next harbour, the next danger, and the next person who can be trusted. Knowledge of routes can be as valuable as the goods themselves. The lesser-known side of these networks is how often they carried fragility along with prosperity. A city dependent on imported tin, cedar, grain, or luxury goods becomes vulnerable when routes break. War, piracy, drought, political collapse, disease, or shifting rivers can sever lines that once seemed dependable. Technologies that require distant materials suffer first. Bronze production can falter if tin supplies fail. Monumental building can shrink if timber routes are cut. Workshops can lose pigments, stones, ores, or skilled migrants. The same roads that carry wealth can carry armies. The same ships that carry ideas can carry plague. Connectivity is power, but it is also exposure. This is why transport technology belongs at the centre of ancient ruins. A ruin is not only a place, it is a former intersection. Its stones may come from one region, its metals from another, its artistic forms from a third, its crops from domestication histories older than the city itself. Every impressive artifact may contain hidden journeys. The strange technology found in ancient ruins is therefore not only a story of invention, but of circulation. Human beings do not merely make tools. They move them, copy them, modify them, and send them into other landscapes where they become something new. And as these networks expand, technology turns inward as well as outward. It does not only move goods across land and sea, it reaches into the body, into pain, illness, injury, beauty, age, and death. The same ancient hands that cut stone and cast bronze also made surgical tools, prosthetic limbs, dental repairs, cosmetics, medicines, and instruments for touching the fragile machinery of human life. The body is the most personal ruin. Long after a city has fallen and its language has grown silent, bones continue to record injury, labour, disease, hunger, violence, healing, and care. A healed fracture can show that someone survived an accident and lived long enough for the bone to knit. Worn joints can reveal repeated work. Teeth preserve diet, stress, migration, and sometimes deliberate repair. Skulls may show surgical intervention. Graves may preserve tools placed near the dead, not only as offerings, but as signs of skill, identity, or treatment. Ancient technology is often imagined as something outside the human body, carved into stone or cast in metal. But some of its strangest and most intimate forms were designed to enter, support, decorate, soothe, or alter flesh. Medicine in the ancient world was never one thing. It was practical care, inherited remedy, ritual action, observation, specialist skill, household knowledge, and belief woven together. A healer might use herbs, oils, honey, beer, wine, resins, minerals, bandages, splints, massage, heat, prayer, incantation, or surgery depending on the culture and the condition. Modern categories again become too narrow. A treatment could be both pharmacological and sacred, both symbolic and physically useful. Honey, for example, appears in ancient medical contexts and has real antimicrobial properties, even if ancient explanations differed from modern microbiology. Willow bark and other plants used in different traditions could relieve pain. Poppy preparations could sedate. The evidence remains incomplete, especially because plant medicines decay and recipes are often preserved unevenly. But what survives suggests that ancient people built large libraries of bodily knowledge through long observation. Surgical tools are among the clearest material traces. Bronze and iron knives, scalpels, forceps, probes, needles, hooks, cautery instruments, and cupping vessels appear in various ancient medical traditions. Some are difficult to identify with certainty because tools could serve multiple purposes, and later interpretation can be too confident. Still, in Greek, Roman, Egyptian, Indian, and other contexts, there is strong evidence for specialized instruments and procedures. These were not modern surgeries performed under sterile conditions with anesthesia as we understand it, and the risks must have been severe. Infection, shock, pain, and blood loss were constant dangers. Yet the presence of refined tools shows that ancient practitioners sometimes intervened directly in the body with confidence born of training. Trepanation, the practice of opening the skull, is one of the most striking examples because it sounds almost impossible to survive. Yet healed skulls from different parts of the world show that some individuals did survive, sometimes for years. The reasons for the procedure varied and remain debated: treatment of head injury, relief of pressure, ritual practice, neurological symptoms, or culturally specific beliefs about illness. No single explanation fully accounts for every case across continents and millennia. What matters is that the bone records both danger and skill. A clean opening with signs of healing is not merely a wound. It is evidence of a procedure, aftercare, and a person who endured it. Prosthetics reveal another kind of ancient ingenuity. The famous artificial toes from ancient Egypt, made from wood, leather, and other materials, show that replacement body parts could be functional as well as symbolic. A missing toe affects balance and walking, especially in sandals, and experimental work has suggested that at least some ancient prosthetic toes may have helped their wearers move. This is a quietly profound technology. It is not built for a king's glory or a god's temple. It is built for the repeated act of taking another step. In a grave, such an object can look small compared with gold or stone, but its human meaning is enormous. Dentistry also appears in surprising forms. Ancient teeth show drilling, filling, wiring, extraction, and attempts at stabilization in different regions and periods. Some early dental interventions were likely painful and imperfect, but they show that tooth pain, infection, and appearance mattered enough for people to attempt repair. In the Indus world, there is evidence of very early drilling of teeth, possibly using bow drills. In Etruscan and Roman contexts, dental appliances and bridgework appear among elites. The mouth, like the city, becomes a site of maintenance. Decay is fought with tools, damage is managed, the human body, constantly wearing down, requires its own engineering. Cosmetics belong in the same story, though they are often dismissed as vanity. In ancient Egypt, eye paints made from minerals such as galena and malachite were aesthetic, social, ritual, and possibly protective in certain contexts. Oils, perfumes, wigs, razors, mirrors, combs, tweezers, and pigment palettes show a technological world of the body's surface. To prepare the face, hair, and skin was to manage identity, status, gender, cleanliness, and sacred presentation. Some cosmetic compounds required mining, grinding, mixing, storage, and trade. A small coal container is therefore a chemical and social object. It is technology applied to the self. Pharmacology is harder to reconstruct because the most important ingredients often vanish. Texts preserve recipes, but identifying plants and minerals across ancient names can be difficult. Residues in vessels, pollen, seeds, and chemical traces help fill some gaps. Ancient Egyptian medical papyri, Mesopotamian tablets, Greek and Roman medical writings, Ayurvedic traditions, Chinese medical texts, and many other bodies of knowledge show complex attempts to classify symptoms, treatments, and bodily processes. Some ideas align poorly with modern anatomy, others contain practical observations that could genuinely help. Scholars still debate how to evaluate ancient medicine without either mocking it as superstition or romanticising it as lost perfection. The balanced view is more interesting. Ancient healing was a mixed field, where careful experience and cultural belief worked side by side. Mummification and embalming show technical knowledge of the body after death. Egyptian embalmers learned how to slow decay through evisceration, drying with natron, resins, oils, wrapping, and controlled treatment of the corpse. The purpose was religious, tied to beliefs about the afterlife, but the material skill was real. Preservation required chemistry learned through practice. Different periods and social classes received different levels of treatment. And not every mummy reflects the same methods. Still, the survival of skin, hair, tattoos, wounds, and disease traces has made mummified bodies extraordinary archives. Death became, unintentionally for modern researchers, a preservation technology. Human remains also show care that leaves no tool behind. A person with severe disability who survives for years must have been supported. Someone with a healed major injury may have been fed, protected, and helped during recovery. This social care is a kind of technology too, though not made of metal or stone. It is organised compassion, practical nursing, and shared knowledge of how to keep a vulnerable person alive. What survives in the record suggests that ancient communities were not only builders of monuments and weapons, they were also caretakers, improvisers, and observers of suffering. The body technologies of the ancient world remind us that invention is not only grand, it is not only walls, roads, ships, gears, and furnaces, it is also a splint tied correctly, a wound cleaned, a herb prepared, a missing toe replaced, an aching tooth drilled, a face painted for protection or dignity, a corpse preserved for eternity. These intimate technologies make the ancient past feel closer, because they begin from needs that have not changed: pain, fear, beauty, disability, aging. And grief are older than civilization. But even the most skillful technologies depend on the worlds that sustain them. Medical schools, workshops, trade in ingredients, scribal traditions, hospitals or healing temples, family knowledge, and specialist lineages can all weaken or disappear. When societies fracture, the technologies of body, water, stone, metal, and memory can become fragile together. The next part of the story turns toward that darker truth: inventions do not always accumulate. Sometimes they vanish. Not because the human mind forgets how to wonder, but because the systems that carry knowledge break beneath war, climate, exhaustion, and collapse. Technology gives ancient societies power, but it also gives them new ways to become vulnerable. A small community that depends on local materials and flexible habits may suffer terribly when drought comes, but it can sometimes move, scatter, adapt, or simplify. A city, by contrast, is heavy. It is tied to fields, canals, roads, storehouses, workshops, walls, temples, records, officials, and expectations. The same systems that allow it to grow can make it brittle when conditions change too quickly. A canal that feeds thousands becomes a point of failure if it silts, breaks, or becomes contested. A trade network that brings tin, timber, grain, and prestige goods becomes a weakness if roads close or ships stop coming. A scribal administration that coordinates labour becomes useless if nobody trusts its authority. The ruins of ancient technology are therefore not only monuments to human skill, they are also warnings about dependence. Collapse is rarely a single event, though later memory prefers simple endings. A city burns, and the fire becomes the story. A palace is abandoned, and the empty rooms seem to explain everything. A final inscription appears, and silence follows. But beneath dramatic endings lie slower processes: soil exhaustion, salinization, drought, political rivalry, migration, epidemic disease, invasion, debt, inequality, resource depletion, administrative overload, and the erosion of belief in institutions. Scholars still debate the causes of many ancient collapses because the evidence remains incomplete, and different regions followed different paths. No single explanation fully accounts for the fall of complex societies across the ancient world. Yet one pattern returns again and again: technology can extend a society's reach, but it cannot make that society immune to the costs of maintaining complexity. Water systems show this fragility clearly. Irrigation can make dry lands bloom, but it can also create long-term problems when salts accumulate in soil or when drainage fails. Reservoirs can buffer drought, but they must be maintained against sediment. Aqueducts can feed cities, but they require constant repair. Wells can sustain neighbourhoods, but they can also become contaminated, depleted, or politically controlled. When the social system that manages water weakens, the physical system begins to decay quickly. A canal does not care that a king has died or a dynasty has changed. It silts all the same. A broken embankment does not wait for political consensus. Water returns to its own logic. The same is true of roads and bridges. An imperial road network may appear permanent when soldiers, messengers, and tax collectors use it daily. But roads are not self-maintaining. Surfaces erode, bridges rot or collapse. Mountain paths are blocked by landslides. Desert routes shift with wells and security. If an empire loses the ability to fund, guard, and repair movement, distance grows again. Provinces become harder to control. Trade becomes riskier. Local economies turn inward. Technologies that once depended on wide connections begin to shrink. A bronze workshop without tin, a palace without cedar, a city without imported grain, an army without reliable roads, all begin to reveal how much of their strength was borrowed from movement. The Late Bronze Age Eastern Mediterranean offers one of the clearest examples of interconnected fragility. Around the end of the second millennium BCE, several palace-centered societies in the Aegean, Anatolia, the Levant, and nearby regions experienced destruction, disruption, or transformation. The details differ from place to place, and scholars continue to debate the roles of climate stress, warfare, internal rebellion, migration, trade breakdown, earthquakes, and political instability. The point is not that one could swept everything away like a single storm. The more unsettling possibility is that a highly connected world suffered cascading failures. Palaces depended on specialized administration, long-distance exchange, elite goods, and controlled labor. When enough links weakened, technologies tied to those systems could disappear or become simpler. Writing systems used by palace bureaucracies vanished in some regions. Monumental building declined. Trade patterns changed. The machine did not merely break, its parts stopped needing one another in the same way. This kind of loss can look like a fall into darkness, but that phrase can be misleading. People survived. They farmed, moved, fought, remembered, adapted, and made new societies. What collapsed was not humanity, but particular arrangements of power and technology. After the decline of Mycenaean palatial centres, for example, people in Greece did not become incapable of thought or craft. But the administrative writing system known as Linear B disappeared because the institutions that used it no longer functioned. A script can die even when people keep speaking. A technology can vanish because its purpose has vanished. In the Maya world, the transformation of many classic period cities also shows the fragility of technological landscapes. These cities developed reservoirs, agriculture, roads, monumental architecture, writing, calendars, and elaborate political systems in challenging environments. Yet between the 8th and 10th centuries CE, many southern lowland centres saw declining monument production, political fragmentation, population shifts, and abandonment or reduction of urban life. Drought appears to have played a significant role in many interpretations, but it was not acting alone. Warfare, political instability, environmental pressure, and social choices all mattered. What survives in the record suggests not the sudden disappearance of a people, but a reorganization of life. Maya communities continued and still continue, but certain urban technologies and political forms were no longer sustained in the same way. Technology can also create appetites that are difficult to feed. Metallurgy requires fuel, especially charcoal, and large-scale production can put pressure on forests. Monumental construction consumes timber, rope, food, and labour. Cities require constant inflows from countryside and trade. Luxury industries depend on rare materials. The more elaborate a system becomes, the more it must draw from beyond itself. This does not mean ancient societies were doomed by technology. And it would be too simple to blame collapse on one resource or one invention. But the costs of complexity are real. Every technical achievement creates a maintenance debt. There is a haunting irony in ruins. The most durable remains may come from systems that were, in life, extremely fragile. Stone temples survive, but the food system that supported their builders failed. Palace walls remain, but the records that organised shipments were smashed or forgotten. Aqueduct arches stand, but the legal and labour structures that kept water flowing are gone. A statue survives without the ritual world that made it powerful. A road remains visible from the air, but no caravan follows it. The artifact endures while the behaviour disappears. Or accelerates this process. Invaders may burn archives, kill specialists, loot metal, destroy dams, cut roads, or deport craftspeople. Sometimes conquerors preserve local technologies because they need them. At other times, violence shatters the institutions that kept knowledge alive. A burned library is not only a loss of texts, it is a break in teaching. A murdered or displaced artisan is not only one death, it may be the loss of a technique if few others possess it. Ancient knowledge was often resilient, but it was not indestructible. Climate stress works more slowly but can be just as severe. A century of reduced rainfall, shifting monsoons, colder seasons, or river changes can undermine agriculture and settlement patterns. Societies with flexible systems may adapt. Those with rigid demands may suffer. The evidence remains incomplete because climate records and archaeological records do not always align neatly, and human choices mediate environmental pressure. Still, ruins across the world remind us that technology is always negotiated with landscape. It can delay crisis, soften it, or redirect it, but it cannot erase dependence on soil, water, fuel, and weather. When ancient technologies vanished, they often left behind legends of a greater past. Later people saw enormous stones, empty canals, unreadable inscriptions, and roads leading nowhere, and they imagined giants, gods, heroes, or lost races. In a way, this was an honest reaction to broken continuity. If the chain of knowledge is severed, the work of ancestors can look inhuman, but the ruins do not speak of vanished superbeings. They speak of human systems that were brilliant and breakable at the same time. This fragility prepares the ground for the most confusing part of the story, the false wonders and the real mysteries. Some objects found in ruins have been pulled into claims of ancient electricity, impossible machining, crystal optics, or lost superscience. Most of those claims collapse under careful examination, yet not every mystery is false. Some artifacts remain genuinely difficult, not because they prove fantasy, but because the evidence is damaged, partial, or still waiting for the right question. The most dangerous ancient mysteries are not the false ones. False wonders can be exciting for a moment, but they usually become smaller when examined closely. The more dangerous mysteries are the real ones, because they require patience. They do not surrender to a single dramatic answer. They sit in the record as damaged objects, incomplete contexts, technical puzzles, or strange survivals from traditions whose working knowledge has partly disappeared. Between honest uncertainty and unsupported fantasy lies a difficult, narrow path. Ancient technology has suffered from both extremes, from those who dismiss too quickly what ancient people achieved, and from those who inflate every gap in evidence into proof of lost superscience. The so-called Baghdad battery is one of the best-known examples. A set of ancient clay jars with copper cylinders and iron rods has been interpreted by some as evidence for electrical batteries in antiquity. The idea is memorable because it seems to place electricity in a world of temples, sandals, and oil lamps. Experiments have shown that similar arrangements can produce small electrical currents if filled with an acidic liquid. But possibility is not the same as historical proof. The archaeological context, exact function, and interpretation remain debated, and mainstream explanations have included storage containers, ritual objects, or items connected with scrolls or other organic contents that did not survive. There is no solid evidence that ancient Mesopotamian or Parthian societies used electricity for lighting, machines, communication, or industrial processes. The object is interesting, but the popular story outruns the evidence. Crystal lenses and ancient optics occupy a similar space. Polished crystals and lenses are known from some ancient contexts, and magnification, burning effects, or decorative uses are possible in certain cases. The famous Nimrud lens, a polished rock crystal object from a Syrian context, has been suggested by some as a magnifying glass or burning lens, while others see it as inlay, ornament, or a crafted object of uncertain purpose. Scholars still debate the interpretation. What can be said carefully is that ancient people understood transparency, reflection, and the visual power of polished surfaces in practical and artistic ways. Mirrors, glass vessels, gemstones, and polished stones show real optical interest. But there is no need to leap from a crystal object to telescopes, microscopes, or hidden scientific revolutions. The evidence remains incomplete, and uncertainty should remain uncertainty. The same caution applies to claims of impossible stone cutting. Around the world, ancient builders drilled, sawed, ground, polished, and shaped hard stone with techniques that can seem baffling at first glance. In Egypt, tubular drilling marks, saw cuts, and fine stone vessels have encouraged claims of advanced machinery. In the Andes, tight-fitting polygonal masonry has been described as if the stones were softened, melted, or shaped by unknown forces. Yet experimental work and toolmark analysis show that abrasives, copper tools, stone pounders, drills, sand, water, time, and skilled labour can achieve remarkable effects. This does not mean every detail is fully settled. Some techniques remain debated, and the efficiency of ancient methods can be difficult to reconstruct. But the central mistake is assuming that if a modern observer cannot instantly imagine the process must have been impossible. There is a quiet arrogance in that assumption. It treats ancient craftspeople as if they were children facing adult problems. In reality, many ancient specialists spent their entire lives mastering a narrow material world with a depth most modern people never approach. A stoneworker who handles granite every day for decades knows things that cannot be learned from looking at a photograph. A potter knows the mood of clay. A metal worker reads heat by colour. A sailor reads wind through skin and rope. A scribe reads administrative patterns invisible to outsiders. Ancient expertise was often local, embodied, and practical. It does not always look like modern science because it was not organised in the same way, but it was knowledge all the same. That said, real mysteries remain. The Antikythera mechanism is real. The exact organisation behind Indus urban standardisation remains unresolved. The full meaning of undeciphered scripts remains unknown. The logistics of some massive building projects still invite debate over ramps, labour organisation, and sequence. The spread of certain metallurgical techniques is still being refined through chemical and isotopic studies. The purpose of some strange artefacts remains uncertain because context was lost during early excavation, looting, or poor documentation. No single explanation fully accounts for all surviving anomalies. The responsible answer is not to flatten the past into complete certainty. It is to distinguish between a genuine open question and a claim that ignores better evidence. Popular theories often gain strength from real gaps. If a script cannot be read, anyone can pretend it says what they want. If a stone is enormous, anyone can declare it unmovable. If a tool is corroded, anyone can assign it a dramatic function. If a monument is aligned with the sky, anyone can turn it into a message from a vanished master race. The absence of an explanation becomes a stage where imagination performs without restraint. But archaeology is not built from gaps alone. It is built from context soil layers, associated objects, tool marks, residues, dates, wear patterns, settlement plans, environmental data, human remains, and comparison with known techniques. A mystery removed from its context becomes almost infinitely flexible, which is exactly why it becomes dangerous. There is also a human reason these myths persist. Many people want the ancient world to feel wondrous, and that desire is not wrong. Ruins should inspire wonder. The problem begins when wonder is made dependent on denying ancient people their own abilities. To say that Egyptians, Maya, Mesopotamians, Inca, Indus craftspeople, Roman engineers, Chinese metallurgists, or Neolithic builders could not have achieved their works without outside help is not respect. It's a failure of imagination disguised as admiration. The better wonder is harder and deeper ordinary human beings, living within the limits of their own materials and beliefs, built things that still challenge modern understanding. Some false wonders also distract from less glamorous but more important technologies. Ancient drains may tell us more about urban planning than a disputed battery. Agricultural terraces may reveal more sustained intelligence than a sensational claim about levitation. A kiln, a loom weight, a measuring rod, a roadbed, a water channel, or a storage jar can be more historically meaningful than an object pulled into fantasy because it looks strange in isolation. The past is full of real technical brilliance, but much of it is practical, patient, and cumulative. It does not always announce itself with mystery. Sometimes it lies underfoot. The final challenge is humility. Modern researchers use tools ancient people could not imagine: radiocarbon dating, satellite imagery, residue analysis, scanning electron microscopy, CT imaging, isotope studies, digital modelling, underwater archaeology, and experimental reconstruction. These tools have solved old puzzles and created new ones. They have shown hidden inscriptions inside corroded fragments, lost cities beneath forests, trade routes inside metal chemistry, ancient diets inside bones, and construction sequences inside landscapes. Yet even with these methods, the record remains partial. Some questions will stay open because the necessary evidence has been destroyed. Others may change with the next excavation, the next scan, the next rereading of an overlooked fragment. So the strange technology found in ancient ruins is not a doorway into fantasy. It is a doorway into disciplined astonishment. Some claims must be set aside. Some mysteries must be left unresolved. Some achievements must be restored to the people who actually made them. And when that is done, the ancient world becomes not smaller but larger. It becomes a place of engineers without modern engines, chemists without atomic theory, astronomers without telescopes, surgeons without antibiotics, administrators without paper files, builders without steel cranes, and inventors whose names were never written down. The ruins remember them imperfectly, but they remember enough. What remains now is to gather the fragments into a final view: the stones, canals, furnaces, tablets, roads, ships, instruments, bodies, and broken machines, not as isolated marvels, but as traces of a long human struggle to make fragile life last a little longer against time. What the ruins remember is not a lost modern world hiding behind the ancient one. They do not remember electric cities buried beneath temples, or vanished factories humming behind pyramid walls, or machines erased so perfectly that only rumour survived. They remember something more human and more difficult to dismiss. They remember that intelligence does not always look like the present. It can take the form of a cord stretched across a foundation, a canal cleared before the flood, a kiln watched through the night, a seal rolled into wet clay, a ship built by eye and tradition, a skull opened with terrifying care, a gear tooth filed by hand, a calendar corrected after generations of watching the moon. The ancient world was not modern, but it was never simple. The strange technology found in ancient ruins is strange largely because it arrives without its original world around it. A drain under an empty street no longer carries household water, so it looks like a feature instead of a daily necessity. A road across a high plateau no longer feels like an imperial artery because the runners, caravans, soldiers, and messengers are gone. A stone circle no longer gathers a community at the turning of the year, so its alignments become puzzles. A tablet covered in numbers no longer controls grain, wages, and labour, so it becomes a museum object. A corroded mechanism no longer moves in a wooden case, so its gears seem like an intrusion from another age. Remove the people, and technology becomes mysterious. Restore the people, and the mystery deepens rather than disappears. The deepest legacy of ancient technology is not any single object. It is the pattern of human beings repeatedly discovering that the world can be persuaded. Stone can be shaped. Water can be guided. Fire can transform. Marks can remember. Roads can shorten distance. Ships can cross fear. Plants can heal or poison. Bones can mend. The sky can be measured. Time can be divided. None of these powers is absolute. Stone cracks. Water escapes. Fire destroys. Writing falls silent. Roads vanish. Roads. Ships sink. Medicine fails. Calendars drift. Yet each attempt leaves a trace of the same stubborn impulse to negotiate with a world that is larger, older, and less forgiving than human desire. There is a kind of humility built into the archaeological record. It tells us that survival is uneven. The gold mask may endure while the wooden cradle disappears. The royal inscription may survive while the worker's joke is lost forever. A palace archive may be preserved only because the palace burned. A tool may vanish because it was valuable enough to recycle. A technology may seem rare because almost every example was made of materials that decay. What survives in the record suggests brilliance, but also distortion. We see ancient societies through the accidents of preservation, and those accidents often favour power, stone, fire, death, and disaster. This is why the most responsible way to approach ancient technology is neither disbelief nor surrender. Disbelief makes the past smaller, reducing ancient people to crude versions of ourselves waiting for progress to rescue them. Surrender turns every uncertainty into fantasy, stealing achievement from real cultures and handing it to imaginary forces. Between those errors is a better path to ask what the evidence allows, what it does not allow, and what remains unresolved. Scholars still debate many details, and the evidence remains incomplete, but uncertainty does not weaken the story. It gives it depth. It reminds us that history is not a locked room with every object labelled. It is a landscape of surviving clues. The ruins also remember consequences. Technology solved problems, but they created new dependencies. Irrigation fed cities, but demanded maintenance and sometimes damaged soil. Metallurgy strengthened tools and weapons, but required fuel, ore, trade, and specialised labour. Writing preserved memory, but tied knowledge to institutions that could collapse. Roads connected regions, but also carried armies and disease. Monuments created permanence, but consumed surplus and labour. Ancient people were not blind to these tensions. Though they understood them through their own worlds of belief and necessity, every technology is a bargain with the future. The bill may come slowly, after generations of success. Yet it would be wrong to end only with fragility. Many ancient technologies did not vanish completely. They changed form, moved into new cultures, and became part of later foundations. Irrigation traditions survived through adaptation. Roads were reused, metallurgical knowledge spread and transformed, calendrical and astronomical observations influenced later science. Medical writings were copied, argued over, corrected, and absorbed into new traditions. Architectural methods migrated through conquest, trade, imitation, and apprenticeship. Even when states fell, people carried skills in their hands. The ruin marks an ending, but not always the end of the knowledge itself. There is also legacy in the landscape. Ancient terraces still hold hillsides. Old canals remain visible from above as pale lines through fields. Roads cut across deserts long after the traffic has gone. Quarry scars remain on mountainsides. Harbour works lie beneath changing coastlines. Mounds cover cities made from the repeated rebuilding of mud brick lives. These are technologies turned into geography. They remind us that humans do not simply inhabit landscapes. They edit them, sometimes gently, sometimes violently, sometimes so successfully that later generations mistake the edited world for nature. The strange technology of ancient ruins finally brings us back to the silent object where the story began. The block, the tunnel, the vessel, the tablet, the gear, the road, the drain. Each one asks to be seen not as an isolated miracle, but as the visible edge of a vanished system. Behind every artifact stand materials, hands, habits, failures, teachers, apprentices, rulers, labourers, traders, farmers, healers, priests, and unnamed observers who watched the world carefully enough to change it. Their tools were not ours. Their explanations were not always ours. Their worlds could be brutal, unequal, superstitious, brilliant, practical, beautiful, and afraid, often all at once. That is what makes them real. In the end, ancient technology does not show that the past was secretly like the present. It shows that the present has underestimated the past. It shows that invention is not a straight road, but a braided river, dividing, drying, flooding, and sometimes disappearing underground before emerging somewhere else. The ruins are not silent because they have nothing to say. They are silent because their language is material, and material speaks slowly. It speaks through wear, alignment, residue, fracture, corrosion, soot, polish, and the stubborn survival of things made by hands that expected a future, though not necessarily us. After the final stone has cooled in the evening air, after the last visitor has stepped away from the ruin, and the shadows have filled the cracks between blocks, the ancient world does not feel quite as distant as it did at the beginning. It feels stranger, but also nearer. Not because its people were secretly modern, and not because every broken object hides a lost machine, but because their hopes were built into things that still remain. They wanted water to arrive when fields were thirsty. They wanted walls to stand. They wanted bodies to heal. They wanted the dead to be remembered. They wanted the sky to make sense. They wanted promises counted, roads cleared, ships launched, fires controlled, and time made less frightening by calendars, rituals, and repeated signs. Much has vanished. The wooden frames have rotted. The ropes have turned to dust. The workshop voices are gone. The instructions have faded, and many of the hands that carried the knowledge were never named. What remains is partial, broken, and often misleading in its beauty. A stone monument can make a civilization seem more stable than it was. A golden object can hide the poverty around it. A clean museum case can remove the smoke, mud, danger, and labour from the thing it protects. Yet even in fragments, the record keeps returning to the same quiet truth. Human beings have always lived by making arrangements with uncertainty. The technologies in ancient ruins are not only answers, they are questions preserved in matter. How did they organise so much labour? How did they learn that heat would release metal from stone? How did they keep a city clean enough to endure? How did they watch the sky long enough to predict its cycles? How many failed attempts lie behind the one object that survived? How much knowledge disappeared simply because it was carried in wood, fibre, breath, and memory? There may never be complete answers. Some archives burned too thoroughly. Some scripts may remain unread. Some machines were melted down before anyone thought to describe them. Some roads now end in sand. But the incompleteness is part of the spell. The ruins do not give the past back whole. They give back edges, traces, impressions, and shadows, enough to show that ancient people were neither helpless nor all-knowing, but inventive in the exact human way, persistent, observant, ambitious, limited and always negotiating with loss. And so the final image is not a pyramid, or a gear, or a polished blade, though each could stand for the story. It is a small light in an ancient workshop at dusk. A person bends over a material that has not yet become what it might be. Clay, bronze, stone, glass, wood, bone, ink. Outside, the city depends on countless other hands. Above, the stars return to their old positions. The maker works carefully, not knowing what will survive, not knowing who may one day wander over it, leaving behind one more trace of the long human attempt to make something last.